I'm very happy to be here. So thank you, organizers, giving me an opportunity to give a talk here. Okay, so I talk on this title. And this is the basic references. And today's talk is mainly based on this paper. It's already in archive. Okay. And there are many other papers. Okay, so here's a picture that explain today's subjects and around subjects of today's talk. First part, I explained these parts. It's related to crystal basis, and I will give some brief review of crystal basis. And after that, I will explain around here. It's related to quiver, Hecke algebras and its categorifications, and also I explain the notion localizations, category of localization. Okay.
May I say something?
From?
There is a simple way to make the screen horizontal and a bit larger.
Larger. That's one. Okay, thank you. So I didn't notice that. Okay, thank you very much. Okay. So yeah, and finally, so I'll talk on the relations, this part and this parts directly. Okay. Okay. So first, we need some preparations. So today's I set this simple real algebras, I think, and the Cartan matrix, and simple roots, simple co-roots, root lattice is a usual setting. I guess, weight lattice, dominant weights, and dual weight lattice. And W stands for the while group for related to G. And UQ of G is the usual quantum algebra generated by the generators EI, FI, and the Q to the H with some usual relations I omit. And UQ minus and UQ plus are the unipotent subalgebras. They are generated by FI, AI respectively. Okay. And the quantum coordinate ring, unipotent quantum coordinate ring AQ of N is defined as a restricted dual of UQ plus of G. A has a such decomposition, so each AQ and beta is just the dual of UQ plus K minus beta. Beta is from here. There exists, it is known that, we're known that embedding of algebra UQ of A and in F star. F star is quantum shuffle algebra, so the product of this algebra is given by so-called quantum shuffle product. Okay. And it is also known that UQ minus and the AQN is isomorphic to each other as a QQ algebra. Okay. Okay, so now we enter the theory of crystal basis. So Cashwar operators on UQ G minus. Here, any element in UQ minus G has a such type of decompositions uniquely. Here, UK is the element in here, kernel EI prime and intersection of UQ minus G. Here I do not say what is EI prime, but it's similar operators of EI. Okay, so then EI tilde is defined, just shift this exponent to K minus 1. And if I tilde also defined this exponent to K plus 1. That's simpler actions. Okay, then the Kashwara show that there exists so-called crystal base of UQ minus. This is a pair L of infinity and B of infinities. Here, why we use the infinity? Because UQ minus is something so-called highest weight module V of lambda. Lambda is the highest weight. And also it's embedded in this one. So in this sense, this one is just obtained some kind of projected limit. We take lambda to infinity. Also, this one is kind of inductive limit. Then so Kashwara showed that there exists also the crystal base L lambda and B of lambda for irreducible modules. But today, so I don't say this one today. I omit this one today. Only explain this situation, B of infinity, L of infinity, and B of infinities. So the definition is like this, L of infinity and B of infinities. So here we consider the operator Fi tildes on U sub U infinity. This is just the unit of this algebra. Okay. Here A, capital A is a local subring of Q at Q equals 0. Okay, so B of infinity is also such a set. Okay. This is an element in here, L of infinity over Q L of infinity. Okay. Then he showed, Kashwara showed that important is B of infinity is just the basis of this vector space, Q vector space. So here this means, here this says that we can see this one, Q goes to 0, then so we call this crystal base. And also important properties here, because B of infinity is just a set. This is a basis, so this is a set. But E tilde act on basis element, and then so we obtain no linear combination, just one element from basis element, basis. Okay? So this is very remarkable property of crystal bases. And also E tilde and F tilde are almost inverse each other. Of course, if it goes to 0, it cannot go back. But if it doesn't go to 0, if I apply E tilde, then we can go back Fi tildes. Then we go Fi tildes, then we can go back by E tildes. So this structure is very, very, very important for this theory. And the crystals is a combinatorial object, so combinatorics here, obtained by abstracting the property of crystal bases. The definitions is like this. Here we prepare the 6 tuple, B, weight, blah, blah, is a crystal base if B is a set, just a set. And also we prepare one extra element, 0. This is outside B. Basically, basis doesn't include 0, so we need 0 outside basis element. And here is the maps, the E tilde and the F tilde here. So the important, so there are several conditions, but the important is here also. It says B prime element in B, and then for any I, one has such relations between F tilde and the E tildes. Okay. So this says that B has naturally a graph structures, an oriented I-colored graph defined by like this. Here is a arrow I is obtained by action Fi tildes. Okay, for example, not this case, but this is a typical crystal graph of B of lambda 1 plus lambda 2. Lambda 1 and lambda 2 are fundamental weight for SL4. This is crystal graph. So this is the highest weight vector, and this is the lowest weight vectors. This case, each vertex is parameterized by Young tableau. Okay, shape is this one, this shape. Okay, and where? Here? No. Here.
Yeah, you have to do something. Your operators 1 and 2. Do they act by values or by cells? Do they permutate cells, or do they change values in your Young tableaus?
Yeah, that's right. Yes. Shape not unchanged. Only the entries just change. Thank you. So here is 1, 1, 2. If you apply if until the here, then so this one goes to 2. Yeah, and then so finally, so you reach to the lowest. The entry is restricted from 1 to 4. 1 to 4. Okay. Okay, so the one important examples today, we take I. It's an index of capital I is an index set of simple roots, And Bi is a crystal. It is each element is parameterized by integer z, and it has following actions by ei tilde and fi tilde like this. It's n go to n plus 1 and n goes to n minus 1. Then the crystal graph is just like this. So straight line, only I, arrow I, only here. This is very simple structures, but it's very important for us today because crystal basis has naturally the tensor product structures. Then we can consider the tensor product. As I said, this is just the direct product, okay? But its structure is simply described by using this function sigma kx on this set. Okay, so this is defined like this. This is a linear function. And this coefficient is coming from the Cartan entry of Cartan matrix. Okay, so here's this is maximum. And this says where is the maximum, the range of maximum. And then this is the rightmost, and this is the leftmost. Then we just fix this one from this function. Then the action by fi tilde and the ei tilde just defined like this. So fi tilde x is just plus 1 here, only here. And ei tilde just minus 1 only here. Okay. So it's very simple. And also we need one other linear function, beta k is just difference of this one. So k plus is the index that's the nearest to k is bigger than, but the nearest index which same the same index ik or il. Okay, this is the differences of sigma k's. This is the beta k of x. Okay, so the application of these crystals is as follows. The Kashmir embedding and pre-header realization. So we have embedding of b of infinity to here, this embedding. Then we can iterate this one according to some sequence of indices. Then we have the following embedding. Fortunately, if we take this sequence as the longest element of while group, of course it's setting with simple case, simple or semi-simple case. Then so this embedding so stops here. So this number is just the length of while group element, the longest element. Then so if we have the image of this embedding, this is isomorphic to b of infinities. So describe this one is so-called pre-header realizations. This is done myself and Andrei Zervinsky. Okay, for example, type A2 case, we take the longest element, longest reduced expressions 1 to 1 in SL3 case. A2 case, SL3 case, yes. Then the image is described like this. Here's 3 entries from Z3, and it is defined by the following inequalities. Okay, tomorrow maybe Yuki Kanakubo will explain this one, I hope. Okay, and then this crystals has a good properties following grade type isomorphism. For example, Cartan data is 1, 2, 3, 4 like this. Then there exists the following isomorphism: 2, 3, 4, 6 isomorphisms. Okay. Then so this says that this crystal, if we take for each while group element W and we take 2 reduced expressions of W, then these crystals is always isomorphic to each other. Okay. Then we call this case, so the I, capital bold I is just the reduced expression of the while group element. Then we call such crystals, this tensor product is called cellular crystals. Because this crystal is obtained from the geometric crystals on Schubert's cell by considering the tropicalizations. Then so we call this cellular crystals, okay? Indeed, oh. Oh, no. So crystals, as I explained, so here is crystals basis like this, B of infinity or B of lambda. This is coming from crystallizations, Q goes to zeros. And other side, BI, is coming from the Schubert cells, that's the tropicalization. So there are two types crystals. It's coming from the modules of UQ minus, UQ, or tropicalizations from geometric crystals. So, but just to corroborate these things, so we have many good things. Okay. And we have shown that this crystal, if we take bold I is reduced expression, so this crystal is connected. Connected means as a crystal graph, connected graph. So this means connected, okay? And now we have subspace HI. HI is just the solution space of this system of equations, beta k x equals 0. So solution, the integer solutions, okay? Fortunately, this has natural z basis, like this, okay? So later we need this one, so, but right now, so why we consider such things? But important is beta k is always 0, so this means, so there's no, the frak, beta sigma k, this is defined the action of ei tilde or fi tilde on bi, just flat. Then so we add this one to other vectors, so then so the action of ei tilde and fi tilde is hi does not affect the action of ei tilde and fi tildes. Okay, anyway, so please remember these values. So later it appear again. Anyway, so important fact is this has such basis. Sorry, and so here lambda I is the fundamental weight, ith fundamental weight. Okay, so this has such following good properties. So for example, first we set BH will be infinity. So H is coming from this HI, okay? This one. So this means just we shift the B of infinity. B of infinity is like this. Then we just shift by H. We have other BH infinity, like this. Then so the number one says that this shift and the action of ei tilde just commute. Okay, this one says. Okay, so this structure just parallelly coming to here. Okay, it's number one. And number two, so this has always non-empty intersections. And finally, this is the most important. So if we consider the all of them, so then we consider the union, or then so we just recover BI. This one is same BI. Okay. So now we enter the next topics, just quiver Hecke algebras. So we prepare the index set I, capital I, and polynomials Qi, J, U, V. It satisfies the following conditions. Okay, then so quiver Hecke algebra, R of beta. Beta is coming from here, Q plus. Is associated with the character matrix A, and the polynomial Qij is the algebra generated by the following generators E nu, xk, tau i's. And they satisfy the following relations. It's really complicated, but important is this E nu says this is just projectors, set of projectors, okay? And then other relations, there are many relations here, okay? Anyway, important is these relations above are homogeneous if we define the degree like this. So in this sense, R of beta becomes Z-graded algebras. Z-graded algebras, okay? So this is important point. because later we need to grading shift functors or something like that. So it is important here or already here. So now I summarize some property of R modules. Sorry. R is just the or summation of direct sum of this R of betas. Okay, this is algebra, also algebras. Okay. Then so Q is just grading shift functor on modules like this, defined like this. And then we also define the convolution product on modules M and N. This is defined like this is usual induce up. And the head. So M nabla N is just the head. Head is modules obtained by quotient by the considering quotient by its radical. And circle is the summation of all its simple modules. Okay, so we use these notations later. And this module is called real if M circle M is again simple, so we call M is real. Of course, if it's not simple, it's called imaginary. And M is isomorphic to M star, then we call this is self-dual, okay? This is the notation and the terminologies. And the important results by Kuanov, Lauda, and Ruquier is we consider the category of finite-dimensional graded modules and category of finite generated graded projective modules. Then they show that, so this Grothendieck ring of R of RG project is isomorphic to UQ minus, and the Grothendieck ring of R of Gmod is isomorphic to AQN. Okay, this is the important results. So to obtain this one, so we need throwing functors EI and FI, capital EI, capital FI. Capital EI defined using projector, and FI is just using convolution Li and M. Li is just a simple R alpha I module, one-dimensional modules. So this action is rather simple, but it's important. Indeed, this plays a role in action on here. Then the action is so-called Q boson actions is also here. So we have the isomorphism between these two objects. Also here, this one. Okay. Then so now we consider the categorization B of infinities. This is done by Lauda and Bajrani. We take B of R Gmod is the family of self-dual simple modules. Self-dual simple modules. Then EI tilde and FI tilde is defined using circle and head, like this. This is the action of casual operators. Okay. Then so they show that this, so I don't say anything on here, but anyway, this 6 tuple holds the crystal structures, and there exists the following isomorphism of crystals from here to B of infinity. This is isomorphic as the crystals. Okay. Okay, so I don't have so much time. Then now we enter the localizations of category. Okay, so we consider the Z graded, lambda is a Z lattice, so lambda graded monoidal category T. Okay, so here is the product star bifunctor circle here. First of all, graded braided is a triple CRC phi. C is the object, and phi is a Z linear map from gamma lambda to Z, and RC it's like R matrix C circle X to X circle C with some cube powers, Okay, and then they satisfy the following commutative diagrams. Then we call this is graded braiders. Okay, then next we define real commuting family of graded braiders. So this triples each is parameterized by index set I, capital I. So this one is called real commuting family of graded breeders in T if C is the object from here, and if I satisfying these conditions. And the important is this one is scalar, and this this is compositions, not convolution product. This is compositions as a map. This is also scalar. Then so we call this, and of course this one satisfies Yang-Baxter equations on Ci, Cj, Ck's. Okay. And also, if we have a real commuting family of graded breeders, we have an object C alpha. Alpha is coming from here, gamma plus. Sorry, I haven't said anything on gamma. Gamma is such these lattice, and gamma plus is this one, positive one part. Okay, then so we have, so later this goes to weight lattice, and this goes to dominant weights. Right now, so we don't say that this one, but later, if we apply this theory to R, algebra R, then so it goes to, gamma goes to P, and gamma plus goes to P plus. Then if we have this one, then first we have this object by considering this isomorphism. Anyway, important is, so we have just accumulate simple one to, then we have C alpha, object C alpha. Okay. Then so now we enter the consideration localization. So here is the real commuting family. Okay, so then we consider the partial order on gamma like this. So their difference is in gamma plus. Okay, so for alpha 1, alpha 2 in gamma, then define d alpha 1, alpha 2, and so on is a subset of this one. Then so pair x alpha and y beta, we consider the such set of morphisms like this. It's really complicated, so just I don't say anything on here. Is some q powers. Q power means just grading shift. Okay. The important result is, so here there exists zeta delta prime. It's from here to here. So this has a structure inductive system. Then so we can consider the inductive limit of this set. Of this one. This one. This one. Okay, now we can define the localizations here. So object T is originally T is the modified monoidal category, and then object T tilde is object T times gamma. Gamma is this one. Gamma is this one. And morphism is just the inductive limit of this one. And the product, tensor product or convolution is defined like this. Simply it's x, y convolution, and alpha, beta, just sum. Okay. So it's like usual fractions. Product of fractions is like that. Okay. Then so they show Kashiwara and so and his collaborators show that T tilde becomes a monoidal category. And moreover, there exists exact monoidal functor upsilon from T to T tilde. Okay. With certain universality, but I meet it, so this one. So anyway, this has some good properties. This is good properties. Anyway, I don't have so much time, sorry. And then so now we apply this one to gmod. Okay. First of all, we need to prepare the modules Li to the n. Is defined like this. We consider the Li. Li is one-dimensional simple modules. We consider their product, n times product, and some q shift, grading shift. Indeed, its q dimension is just q factorial. So this is Pryor's role of q factorial in usual quantum groups theories. Okay, here we consider the fi tilde n to m is like this. Here's the head of this and this convolution product of these things. And we set mk is like this. Here's lambda is dominant weight. Okay. Then now we define the determination modules is defined like this. One is the unit object in T, RG mod. This is one-dimensional trivial module. Then so we are applying these functors like this. Then we call this is determination modules, depend on Y group W. Indeed, this corresponds to so-called generalized minors. Generalized minor is and also we have other operator fi star. So today I don't say anything on, but using fi star, so we can change here. Then so it's really the generalized minor. So anyway, so I don't say anything on this one. Anyway, using this one, so we can consider the localizations of RG mod. Non-degenerate C is such one is non-zero, and we set C lambda. This is the determination module corresponding to longest while group element, and this is fundamental weight. Especially, so we set Ci is corresponding to lambda I case, fundamental case. Then define the function phi Ci is like this. Then this one, here's Ci is coming from here. This is determination modules. And RCI I omit the definitions, but there exists, and the phi is this function. Then this one is non-degenerate real commuting family of graded breeders in RG mod. Then, so we can localize this category to here, this one. Okay. Then this Grothendieck ring of this category defines a localized quantum coordinate ring, AQN tilde. Indeed, its structure is simply like this. We get this one is isomorphic to so-called the left ring of quotient of ring K RG mod. With respect to the multiplicative set, this is the denominator. This gives the denominator of these localizations. Okay. Then they have good properties. For example, this natural functor, it's called localization functor, is exact. And also, this one is abelian, then this category is also abelian. Okay, and then, so there is other good properties, but the last one is important for us, because any simple object in this localization category, there exists simple module S and weight lambda, then this one is always isomorphic to this form. But this expression is not unique. It's like, you know, fractions 1 over 2 equals 2 over 4 or 3 over 6 or like that. So expression not unique, but there exists such expressions always. Okay. So using this, we can define the crystal structure on our tilde gmod. Okay, so omit. Anyway, so we take this one. This family is the family of simple. No. Self-dual simple modules in our tilde gmod. Okay. Then we define the Cashwar operator fi tilde ei tilde like this. Here we have this expression, as I said here. Any simple object has a such expression. Then fi tilde indeed act on here, not here. Then this action is given by Lauda and Bajrani already. So this action is very simple. But ei tilde is really different from fi tildes. If EIS not 0, it's okay. So we similarly to FI tilde, so we act EI tilde on S. But if it's 0, then we just borrow one module from here. Lambda I star. Borrow, and then also act EI tilde here and consider the conversion product. This gives the action with EI tildes. So this part is different from the non-localized situations. Okay. Before localization, so if under this situation, so it goes to zeros. Okay. I star is usual how to say automorphism. I minus I star is defined like this. Okay. Then the crystal structure is also given by this one, so I don't say anything on that. But then so I show that. So this 6 tuple is a crystal. To show the most difficult point to show this theorem is very definedness. As I said, this expression is not unique. So the action or other data does not depend on the expression. So this is the most difficult point in these proofs. Okay. And okay, so then so just remember this HI, what it is. It is just the solution space beta k equals 0. Okay, so this has such basis. Okay. So the important lemma is this HI or H lambda is obtained by this form. This one is the same, this one, okay? So this formula is really similar to this one. Okay, so this means H lambda I corresponds to determinantial modules by this correspondence. Where? Yeah, here. Okay. So by these formulas, so this one, this determinantial module corresponds to this basis element. If I lambda is I case is this determinantial modules. No, sorry. Okay. So here 1 is just correspond this element in tensor product. Then finally we have the following correspondence. Take simple modules from here. Then we send this to here.
You have 5 minutes.
Okay. Psi S is defined by Lambda and Bajrani. Here this isomorphism is given by Lambda and Bajrani. So we use this one here, and this one corresponds to here. Okay. Then this gives us the isomorphism between the crystal B of gmod tilde and cellular crystals. Okay. So 5 minutes. Okay. 4. Okay. So, as I said, so procedural realization, it's like if we consider the lattice BI, then we take some domain. This one is B of infinities. Then we forget around here. But these parts is recovered by localizations again from here. This part is given by Lambda and Bajrani, And by considering localizations, we can recover around these parts is again. Okay. This is localization. So, and then I don't have so much time. So, what's this? This category has a good property, so-called rigidity. Rigidity means, how to say it, I don't have so much time. So anyway, there exists some dual. For any x, object x, there exists right dual and left duals. The important feature is for x is simple, then dx or the inverse x is also simple. Then so we can, the problem is we can describe this one in Bi, cellular crystals. And next problem, I omit. And final problem is, so today's setting is simple or simple setting, but we can consider this situation symmetrical or Katsumudi settings, okay? Then for any wide group element W, there exists for subcategory CW. So I don't say the definition with CW, but anyway, so this permits the localizations. The question is, this has also crystal structures or not? And if so, this is isomorphic to cellular crystal also. But of course, this one is, you know, in general Katsumudi settings, there is no longest element. So this is not, how to say it? No,
it's a good time.
Okay, okay.
Good moment to stop.
Okay.
If you don't mind.
Yeah, okay. So, yeah.
We thank the speaker, and of course, now is the time for questions or remarks. Gleb?
Is there some combinatorics like I-trails for this determinant modulus?
Oh. Yeah, possibly, but I'm not sure how to do it, but yeah, possibly, yes.
Marek?
So you present very nice Q-boson relation model.
Yeah.
And of course we are doing with Roland Speicher 30 years ago construction, but for us it was important that that elements of that AI and Fj will be self-adjoint each to other, and realization were on a Hilbert space. Your situation is very algebraic, or you have also this chance in your model to add scalar product that your operators or that quadrational annihilation, let's say in Q case, will be is very important with corresponding.
Yeah, of course. Yeah, originally it's algebraic definitions, but if you consider the quantum coordinate ring, it's like a space of functions. Like so, we can also define the Q-boson operators on that spaces. So, how to say? So, if you have some in a product or yeah, possibly, yeah. I'm so sorry, I'm not sure, but yeah.
Especially for us, it's interesting Q of modulus 1 because this physics called this anionic relation and have some chemical, physical interpretation. Also, you can use Q of modulus 1, complex numbers, or your Q is abstract element.
Abstract, yes, but how to say? Yes, right now, yes.
Okay,
Thank you very much.
There is a room for last question or remark. So if there is none, so thank you very much, and also thank you for.
Thank you.